Welcome. This video will work through the proof of the derivative of exponential functions as well as that of logarithmic functions. So to begin, I want to look at the function y equals 3 to the x. And most calculus students, when presented with this equation, would think that they would have to use the power rule to find the derivative, and they would say the derivative is y prime equals x times 3 to the x minus 1. And if you look at this seems, what's wrong with this, is what a lot of students would ask. And, well, let's think about what this derivative tells us. It would tell us that when x were negative, this entire expression, the slope of the original function would be negative, because this part here would be negative and this part here would be positive. It also says that when x equals 0, the slope would be 0. And if we think a little bit about a graph of an exponential function, y equals 3 to the x. Ta-da, here's the graph. Fix this here. So if we look at this graph, we can realize a couple things. One is this function y equals 3 to the x is always increasing. Therefore, the slope, the y prime, is always going to be positive. Also, it looks like when x is a really big negative number, the slope is close to 0. And as is over here, and as x gets bigger, the slope gets larger and larger and larger. So what would the graph of y prime have to look like? Well, it looks like it'll start at 0 and make its way to something larger and larger and larger and larger. So it could look like that, or it could look something like this. We don't know. At this point, we don't know. But one thing we can hypothesize is that the graph of the derivative of an exponential function looks a lot like some other exponential function. Some sort of stretch, vertical stretch of that exponential function. So the question is, well, what is it? Well, what will help us to figure it out is to go back to the definition of the derivative. So here we are. According to the definition of the derivative of b to the x is equal to the limit, as h goes to 0, of b to the x plus h minus b to the x all over h. This doesn't really answer the question, but what we can do is we can manipulate this a little bit. What can we do to this? The first thing we can do is rewrite b to the x plus h as b to the x times b to the h. And then what you'll notice, there is a b to the x here and a b to the x there. So what we'll be able to do is to factor out a b to the x out of the entire limit, because x has nothing to do with the limit as h goes to 0. Okay. So what does this tell us? Well, this tells us a little something here, that the derivative of b to the x is equal to b to the x times some limit. And if we look at this limit, it depends upon one thing. It depends upon b. And depending on what b is, this limit here will have some value. We don't know what that value is, but what this tells us is that the derivative of b to the x equals b to the x times some number that depends upon b. So this limit here will be some constant that depends upon the value of b. So what this means is that the derivative of b to the x is equal to b to the x times some constant, which is just a vertical stretch of b to the x, just as we hypothesized. The question is what is this? What number does that turn out to be? Well, let's take a look. Back to the graph. All right, so what we have here in the graph that just was pasted here is a graph of y f of x equals b to the x, which is in blue, as well as its derivative, f prime of x, which is in red. And one thing I can do is see what happens when the value of b changes. You'll notice, when b is between 0 and 1, it appears the slope is negative, and as the value of b gets bigger, the slope changes. But there is a point where they appear to be the same. That number looks to be around 2.71-ish. Very familiar. That seemed to be around e, that number that you learned about in pre-calculus class. Now, what I've put on here is a point at some random number c, and you can see here is the value of f at that value, that x value, and here's the value of f prime at that x value. And you'll see that as c changes, not surprisingly, these y values change as well. However, if I take the ratio of these two numbers, f prime at that x value divided by f at that x value, I get a number. Now, what will happen if c changes? Well, c is changing, and that number, that ratio, is not changing. And that should not surprise you at all. Why not? Well, here is the ratio. F prime of x divided by f of x is this value, which we found up here. B of x times that, b to the x times that limit, divided by b to the x. And these b to the x's will cancel out, so I get that. So this number here, this number right here, is that ratio, is that limit as h goes to 0 of b to the h minus 1 over h for this particular b value, 1.6379. Now let's go back to the graph. And what we're going to do here is we're going to keep track of the value of the ratio for different values of b. And one way to do that here is to create a table of values for of that ratio. And what we'll do is we'll collect a sampling of 25 different ratios at 25 different b values. So all this is doing right now is keeping track of the b value and then the ratio at that particular b value. And this will help us. And a couple things we do know, we've seen to have found, is that when it's around e, the ratio is about 1. We've also found that when it's between 0 and 1, the ratio is negative. So let's plot this data, put the b on the x-axis and the ratio on the y-axis, and this graph here looks kind of familiar. And the question is what graph is that? Well, looks a lot like a log graph. And there we go. The natural log of x seems to fit very nicely, but how do we know that this limit here is going to be equal to the natural log of the b value? Well, we're almost there. So what I'm going to do is get rid of this graph here, and what we're going to do is come up with a new definition of what e is. At this point, you might remember from your pre-calculus class some sort of limit as n went to infinity, something to do with compounding growth, compounding continuously. We'll come to that definition in a few minutes. But first thing I want to do is come up with another definition. And I'm going to define it as is the number such that this limit is equal to 1. Let's just e be the number that makes this limit equal to 1. That is, it'll be the number where the derivative, if b is the base, the derivative of e to the x will be e to the x. We'll just define it that way, that this limit will be 1. So let e be the number that makes this limit equal to 1. And therefore, this is going to be the case. The derivative of e to the x will equal e to the x times that limit, but since we know that limit's 1, that the derivative of e to the x is e to the x. So e is the number. We've defined e as the special number which makes this true. There is going to be some number where the derivative, some base, where the derivative is going to equal itself, and we're going to let that be e. We're going to define e to be that number. So how does this help us to figure out that the multiplier is going to be the natural log of the base? Well, let me remind you of something that you probably learned in pre-calculus. All right, for example, that 3 is equal to e to the natural log of 3. What does that mean? Well, remember what the natural log means. This is the natural log of 3 represents the number that you have to raise e to get 3. So when I raise e to the number that I have to raise the number that I have to raise e to get 3, well, I'm going to get 3. E to the number that I have to raise e to get 3 is going to be 3. Okay, so how does that help us? Well, it means that, just erase some of these things here, it means that 3 to the x would be equal to e to the natural log of 3 to the x, which is then e to the natural log of 3. E to the x times the natural log of 3. Or, more generally, that b to the x is equal to e to the x times the natural log of b. And that's what's going to help us. Because the derivative of b to the x is the same thing as the derivative with respect to x of e to the x times the natural log of b, which is equal to e to the x natural log of b times the natural log of b by the chain rule. The derivative of x times the natural log of b is just the natural log of b, because x, it's basically just x times a constant. And when you have a constant times x and you take the derivative, you get the constant, in this case natural log of b. And then if we rewrite e to the x times the natural log of b, we get b to the x times the natural log of b. And look at here. Here we have it. The derivative of b to the x is equal to b to the x times the natural log of b, which is exactly what we wanted to prove. Which is that this limit here, the limit as h goes to 0 of b to the h minus 1 over h is equal to the natural log of b. That constant multiplier is the natural log of b. And once we know that the derivative of e to the x is itself, that the derivative of e, that is, the derivative of e to the x is equal to e to the x, we can quickly derive the derivative of this function, y equals the natural log of x. And that's because y equals e to the x and y equals the natural log of x are inverses of each other. And another way of writing y equals the natural log of x is this. E to the y equals x. And why is that helpful? Well, up here where we had something that we did not know how to take the derivative of, here we have something we do know how to take the derivative of. We can take the derivative implicitly of e to the y equals x. And if we take the derivative, of both sides with respect to x, we see that the derivative of e to the y is e to the y, is itself, but then times by the chain rule the derivative of that exponent, which is dy dx. And then the derivative of x is equal to 1. So we get e to the y times dy dx is equal to 1. And if we solve for dy dx, we get that dy dx is equal to 1 over e to the y. But what is e to the y? Well, if we look up a little further up the page, we see that e to the y is equal to x. And therefore, dy dx is equal to 1 over x, which means the derivative of y equals the natural log of x is equal to dy dx equals 1 over x. Or more succinctly, the derivative of the natural log of x is equal to 1 over x, which is pretty amazing because if you look at this, this links together logarithmic functions, which are related to exponential functions, with rational functions. These functions are much more related than you ever thought they were. And what if you have a natural log whose base is not e? You have the natural log of some random number, some log base b of x. What is its derivative? Well, there's a couple ways of attacking this. One way is just to rewrite this equation a little differently. And that is as b to the y equals x. And then take the derivative of this equation implicitly. And applying what we already know to be true, that the derivative of b to the y is equal to b to the y times the natural log of b times, by the chain rule, dy dx. And the derivative of x is 1. And if we take this and we solve this equation here, this third equation here, for dy dx, we'll see that dy dx is equal to 1 over b to the y times the natural log of b. But what's b to the y? Well, b to the y is x. So if we make that replacement, we get that dy dx is equal to 1 over x times the natural log of b. That is, the derivative of the log base b of x is equal to 1 over x times the natural log of b. So in summary, these are the 4 derivatives that we just proved. Just arrange these a little bit here. And there are those 4 derivatives. 4 pretty useful ones as you continue on. Now, and there will be another part of this video where I attack this from a different direction, a completely different direction. These were all based upon our definition that e was the number that made the derivative of the exponential function equal to itself. And that's it. That's all we know what e is. But I can tell you that that definition that you learned in pre-calculus, that the definition that we used in this proof that we went through actually implies the definition that you learned in pre-calculus. And to see that, well, you'll have to watch my derivative from the other perspective, starting with the derivative of the natural log of x, which there'll be a link to in the comments below, or also at the end of the video there'll be a link to it. So hope you found this video helpful, and it helped clear up at least one version of a proof of these various different derivatives.